Look at any deep space image and it quietly tells you something that feels obvious. Everything is out there, and we are right here in the middle of it. Galaxies spread in every direction. No edge, no preferred side. Just a kind of perfect symmetry, like the universe arranged itself around us. That feeling is hard to shake. Even if you know better, it still looks like we're at the center. But that picture is lying to you. What you're actually seeing is not the universe laid out in space. You're seeing a boundary in time. Light doesn't travel instantly. It moves at a fixed speed, which means every distant galaxy comes with a delay. When you look far away, you're looking back. Not metaphorically, but literally. A galaxy a billion light-years away is being seen as it was a billion years ago. So when telescopes like the James Webb Space Telescope push deeper into space, they're not just extending our view outward. They're peeling back earlier and earlier moments in cosmic history. Webb has already spotted galaxies that existed only about 280 million years after the universe began. That's not just far, that's early. And here's the key part. No matter where you are in the universe, you would see the same thing. A sphere of visible galaxies around you, a horizon in every direction, a sense that you are at the center. Not because you are, but because light has only had so much time to reach you. So the center you see isn't a real place in space, it's the limit of your view. And as Webb pushes that limit farther, the illusion doesn't disappear. It gets stronger. You've been lied to about the shape of the universe. For decades, textbooks showed a smooth, expanding cosmos. Simple, right? Wrong. James Webb Space Telescope data suggests something far stranger. Forget the uniform expansion we were taught. The data reveals massive, unexpected structures. Filaments of galaxies stretching billions of light-years. Voids so vast, they defy explanation. Are these anomalies or the true shape of the universe finally coming into focus? The illusion of uniformity is shattered. The evidence shows we might need to rewrite everything. 95% of what we thought we knew about the universe's shape relied on a single critical assumption, that it's fundamentally flat, like a sheet of paper extending infinitely in all directions. Turns out that might be a convenient but ultimately misleading oversimplification. The idea of a flat universe stems from observations of the cosmic microwave background, or CMB. This is the afterglow of the Big Bang, the earliest light we can detect. And for a long time, the patterns in the CMB seem to suggest a flat geometry. Think of it like this. If you shine a flashlight through a flat lens, the light will travel in straight lines. That's what we expected to see with the CMB. But what if the lens isn't flat? What if it's curved like a giant magnifying glass? Then the light would bend, distorting the image we see. The James Webb Space Telescope is giving us the tools to examine the CMB's patterns in unprecedented detail. And what we're finding is unexpected. The flatness of the universe hinges on its density. Imagine tossing a ball into the air. If gravity is too weak, low density, the ball escapes into space. If gravity is too strong, high density, it falls back down quickly. Only at a very specific density will the ball hover, perfectly balanced. This critical density dictates whether the universe is open, expanding forever, closed, eventually collapsing, or flat, balanced on a knife's edge. For years, observations suggested the universe was remarkably close to this critical density, thus implying flatness. But Webb's observations are throwing a wrench into this neat picture. The telescope is detecting structures that are far too large and massive to fit within the standard flat universe model. These structures, sometimes called large quasar, groups are collections of quasars, supermassive black holes actively feeding at the centers of galaxies, clustered together over vast distances. Some of these groups span billions of light-years, dwarfing anything we previously thought possible. Their sheer size and mass challenge the idea of a uniformly expanding flat universe. Consider these filaments of galaxies. They're like cosmic threads stretching across the void, connecting clusters of galaxies in a vast network. Webb is revealing that these filaments are denser and more extensive than our simulations predicted. In a flat universe, gravity should have slowed their formation, preventing them from growing to such colossal sizes. And then there are the voids. These are regions of space almost completely empty of matter. In a flat universe, these voids should be relatively small and evenly distributed. But Webb is finding voids that are enormous, some spanning hundreds of millions of light years, and their distribution seems far from uniform. This unevenness suggests that the universe's expansion isn't as smooth and predictable as we thought. So, what does this all mean? It suggests that our assumption of a flat universe might be an illusion, a simplification that no longer holds up under closer scrutiny. The universe might actually be curved, either open or closed, and the massive structures Webb is revealing are providing us with the first real clues to its true shape. These findings aren't just about tweaking a few parameters in our models. They challenge the very foundations of our understanding of cosmology. If the universe isn't flat, then our calculations of its age, its expansion rate, and its ultimate fate all need to be re-evaluated. Think of it like navigating with an outdated map. You might think you know where you're going, but if the map is wrong, you'll end up in the wrong place. The flat universe model has been our map for decades, guiding our understanding of the cosmos. But Webb is showing us that the map might be inaccurate and we need to draw a new one. This isn't to say that everything we know is wrong. The Big Bang Theory, the expansion of the universe, the laws of physics, these remain solid foundations. But the details, the nuances, the precise shape and evolution of the cosmos, these are now open questions, ripe for re-examination. The illusion of flatness has been a comfortable one. It allowed us to build simple, elegant models that seem to explain the universe. But the universe, as Webb is revealing, is far more complex and mysterious than we ever imagined. Further examination revealed that these unexpected structures aren't just statistical anomalies. They're consistently appearing in Webb's data across different regions of the sky. This suggests that they're not random fluctuations, but rather fundamental features of the universe's architecture. This means that the standard model of cosmology, the theoretical framework that describes the evolution of the universe, needs a major overhaul. The model assumes a flat universe dominated by dark matter and dark energy, with galaxies forming gradually over billions of years. But the massive structures Webb is seeing suggest that galaxy formation happened much faster and more efficiently than the model predicts, and that the distribution of matter in the universe is far more uneven than we thought. The implications extend to our understanding of dark matter and dark energy. These mysterious substances make up the vast majority of the universe's mass and energy, but we know very little about them. If the universe isn't flat, then our calculations of the amounts of dark matter and dark energy need to be revised. And if galaxy formation happened faster and more efficiently, then the roles of dark matter and dark energy in this process need to be re-evaluated. Here's what's wild. We might be on the verge of a new cosmological revolution, a paradigm shift that transforms our understanding of the universe. Webb's data is challenging our most basic assumptions and forcing us to confront the possibility that the cosmos is far stranger and more complex than we ever imagined. What if the flatness problem is just one piece of a much larger puzzle? How did we get this so wrong for so long? It's not just a minor tweak needed for the standard cosmological model. It's potentially a fundamental rethinking of everything we thought we understood about the universe's shape and its evolution. The James Webb Space Telescope, with its unprecedented ability to peer into the distant past, has essentially thrown a wrench into our long-held assumptions. These unexpected discoveries from Webb aren't just about a few oddball galaxies or peculiar structures. It's about a consistent pattern of observations that challenge the very foundations of our cosmological understanding. Let's examine what these discoveries actually are. One of the most significant findings is the presence of unexpectedly massive and mature galaxies in the early universe. According to the standard model, these galaxies simply shouldn't exist yet. There hasn't been enough time since the Big Bang for them to have formed and grown to such colossal sizes. The problem? These galaxies appear to be far more evolved than our current models allow. We're talking about galaxies with well-defined spiral arms, supermassive black holes, and populations of old red stars, all characteristics that should have taken billions of years to develop. Yet Webb is seeing them at redshifts that correspond to epochs just a few 100 million years after the Big Bang. It's like finding fully grown oak trees sprouting from the ground just days after a forest fire. Further examination revealed a second major surprise, an abundance of supermassive black holes in the early universe. These behemoths, millions or even billions of times the mass of our Sun, are found lurking at the centers of these early galaxies. The Standard Model struggles to explain how these black holes could have grown so large so quickly. Black holes typically grow by accreting matter from their surroundings, a process that takes time. But these early black holes seem to have reached their enormous sizes in a cosmic blink of an eye. Scientists discovered that these observations point to a need for new physics, or at least a significant revision of our current understanding of black hole formation and growth. One possibility is that these black holes formed directly from the collapse of massive clouds of gas, bypassing the slower accretion process. Another possibility is that they grew at a much faster rate than we previously thought, perhaps by merging with other black holes or by consuming vast amounts of dark matter. This means that the distribution of galaxies in the early universe is far more clustered and uneven than our models predict. We expected to see a gradual increase in galaxy density over time, with galaxies forming more or less uniformly throughout space. Instead, Webb is revealing that galaxies were already congregating into large structures very early on. This suggests that the universe may have been more lumpy from the very beginning, with some regions being much denser than others. The implications extend to the nature of dark matter, the mysterious substance that makes up about 85% of the universe's mass. Dark matter is thought to play a crucial role in galaxy formation, providing the gravitational scaffolding that allows galaxies to coalesce. If the distribution of galaxies in the early universe was more uneven than we thought, then our understanding of dark matter's role in this process needs to be revised. Perhaps dark matter interacts with ordinary matter in ways we don't yet understand, or perhaps its distribution is not as uniform as we assume. These discoveries also challenge our understanding of dark energy, the even more mysterious force that is causing the universe to expand at an accelerating rate. Dark energy makes up about 70% of the universe's total energy density, yet we have almost no idea what it is. If the universe isn't flat, then our calculations of the amount of dark energy need to be adjusted. And if galaxy formation happened faster and more efficiently, then the influence of dark energy on this process needs to be re-evaluated. Consider that the flatness problem itself might be a symptom of a deeper issue with our understanding of gravity. General relativity, Einstein's theory of gravity, has been incredibly successful in explaining the behavior of the universe on large scales. However, it may break down under extreme conditions, such as those that existed in the early universe. Perhaps a modified theory of gravity is needed to explain the observed flatness of the universe and the accelerated expansion. Here's what's wild. These are not isolated findings. They consistently appear in Webb's data from different regions of the sky and at different wavelengths. This strengthens the case that they are not random fluctuations or observational errors, but rather fundamental features of the universe's architecture. The scale of this discrepancy and the consistency of these findings is what makes the challenge so significant. We're not talking about minor adjustments to existing models. It's about potentially rebuilding the entire framework. These Webb discoveries force us to confront the possibility that our current understanding of the universe is incomplete or even fundamentally flawed. The assumptions we've made about the universe's shape, its composition, and its evolution may need to be re-examined in light of this new evidence. This could lead to a new era of cosmological research, one that is driven by observation and experimentation rather than by theoretical preconceptions. The analysis continued, with scientists scrambling to reconcile these new observations with existing theories. Some are proposing new models of galaxy formation that incorporate the effects of early supermassive black holes and more realistic distributions of dark matter. Others are revisiting the fundamental assumptions of cosmology, questioning the validity of the flatness assumption, and exploring alternative theories of gravity. What emerges from this period of intense scrutiny will likely reshape our understanding of the cosmos for decades to come. The implications extend beyond the realm of cosmology. A deeper understanding of the universe's shape and evolution could have profound implications for other areas of physics, such as particle physics and quantum gravity. It could also shed light on some of the deepest mysteries of existence, such as the origin of life and the nature of consciousness. If the universe is not what we thought it was, then our place in it may also be different. And then, the next set of data dropped. This kept me up last night. The idea that everything we thought we knew about how galaxies form, how they evolve, could be completely backwards. It's a staggering thought, honestly. So, what exactly is making cosmologists lose sleep? It boils down to the maturity of galaxies observed in the early universe. According to the Standard Model, galaxies should start small and gradually grow over billions of years, merging with other smaller galaxies, slowly building up their mass and complexity. We expect to see young, relatively disorganized galaxies in the early universe, but Webb is showing us something different. It's revealing fully formed, mature galaxies existing much earlier than they should. Galaxies with well-defined spiral arms, central bulges, and even evidence of supermassive black holes already in place. This is like finding fully grown adults in a kindergarten class. It just doesn't fit. Let's examine the implications. If these galaxies were indeed fully formed so early in the universe, it suggests that the processes that govern galaxy formation are far more rapid and efficient than we previously thought. This could mean that our understanding of the role of dark matter, gas accretion, and star formation in galaxy evolution is incomplete or even fundamentally incorrect. One potential explanation is that the early universe was simply a more efficient galaxy-building environment. Perhaps the density of matter was higher, or the conditions for star formation were more favorable. However, this explanation raises further questions. Why were these conditions so different in the early universe? And why did they lead to the formation of mature galaxies so quickly? Another possibility is that our understanding of the distances to these early galaxies is flawed. If they are actually closer than we think, then they would also be younger and less massive, which would alleviate some of the tension with the Standard Model. However, independent measurements of the redshifts of these galaxies, which are used to determine their distances, seem to confirm that they are indeed as far away as we think they are. The presence of supermassive black holes in these early galaxies also poses a significant challenge. According to the Standard Model, supermassive black holes are thought to form over billions of years as matter gradually falls into a central region and collapses under its own gravity. But if these galaxies formed so quickly, how did their supermassive black holes have time to grow to such enormous sizes? Some scientists are proposing that supermassive black holes may have formed directly from the collapse of massive gas clouds in the early universe. This direct collapse model could potentially explain the rapid formation of these black holes, but it also requires very specific conditions that may not have been common in the early universe. Others are suggesting that the early universe may have been seeded with intermediate mass black holes, which then merged and grew over time to form the supermassive black holes we see today. However, there is currently little evidence to support this hypothesis. It's also worth noting that the Standard Model of cosmology is based on the assumption that the universe is homogeneous and isotropic on large scales, meaning that it looks the same in all directions and at all locations. However, some scientists are questioning this assumption, suggesting that the early universe may have been more inhomogeneous than we thought. If the early universe was indeed more inhomogeneous, this could have led to the formation of structures, such as galaxies and supermassive black holes, much earlier than predicted by the Standard Model. However, this explanation also requires a significant revision of our understanding of the universe's initial conditions. Here's what's wild. Some researchers are even exploring alternative theories of gravity, such as modified Newtonian dynamics, MOND, which propose that gravity behaves differently on very large scales than predicted by Einstein's theory of general relativity. These theories could potentially explain the rapid formation of galaxies and supermassive black holes without the need for dark matter or other exotic physics. However, MOND and other alternative theories of gravity face significant challenges in explaining other cosmological observations, such as the cosmic microwave background and the large-scale distribution of galaxies. So, while they remain a topic of active research, they are not currently considered to be the leading explanation for the Webb discoveries. The implications extend beyond galaxy formation. If our understanding of galaxy formation is wrong, it could also have implications for our understanding of the formation of stars and planets. Stars are born within galaxies, and their properties are influenced by the environment in which they form. If galaxies formed differently in the early universe, this could have led to the formation of different types of stars and planets than we see today. It's like a cosmic domino effect. One wrong assumption at the top and everything else falls apart. This is not to say that the Standard Model of cosmology is completely wrong. It has been remarkably successful in explaining many observations of the universe. But the Webb discoveries are forcing us to confront the possibility that our current understanding is incomplete and that we may need to revise some of our most fundamental assumptions. The analysis continued, with scientists focusing on simulations and comparisons. What if the galaxies aren't necessarily forming backwards, but something else is skewing the data? What if we're misinterpreting the light? December 2022. The first detailed spectra from the James Webb Space Telescope started flooding in. Astronomers were eager to see the chemical composition of distant galaxies, hoping to confirm their age and distance. What they found, however, threw a wrench into everything. To understand why, we need to talk about redshift. It's the cornerstone of how we measure cosmic distances. Think of it like this. Light from distant objects gets stretched as the universe expands. This stretching shifts the light towards the red end of the spectrum, hence the term redshift. The farther away an object is, the more its light is redshifted. Simple, right? Well, that's what we thought. Redshift is directly proportional to distance, meaning a higher redshift should automatically mean a greater distance. For decades, this relationship has allowed astronomers to map the universe, determining the location and age of countless galaxies. It's been a reliable tool until Webb came along. The problem? Webb was showing galaxies that appeared surprisingly bright and well-formed at redshifts that should have corresponded to much earlier times in the universe. Galaxies at those redshifts should have been faint, small, and relatively unstructured. The intensity of the light being emitted by these young galaxies was far too bright to be so far away. If their redshifts were accurate, these galaxies would need to be impossibly luminous, far brighter than anything we've ever observed in the local universe. This brightness suggested something was fundamentally off with our understanding of cosmic distances. It gets weirder. The spectral lines themselves, the unique fingerprints of elements within these galaxies, were also sharper and more defined than expected. In young galaxies, you'd anticipate a chaotic mix of elements leading to blurry spectral lines. But Webb was seeing galaxies with relatively clear and distinct spectral signatures, implying a level of chemical maturity that shouldn't have been possible so early on. The initial reaction was disbelief. There were concerns about calibration errors, instrumental glitches, anything that could explain away the anomalous data. Teams of scientists spent months meticulously checking and rechecking the Webb data, comparing it to observations from other telescopes and running simulations to rule out any possible systematic errors. But the results consistently pointed to the same conclusion. The galaxies were too bright, too well-formed, and too chemically mature for their supposed distances. The redshift measurements simply didn't align with the physical properties of the galaxies. This discrepancy ignited a debate within the astronomical community. Was redshift as straightforward as we thought? Could there be other factors affecting the observed redshift values, leading to an overestimation of distances? Could the early universe have been fundamentally different than our current models suggest? One possibility is that there's more dust in these early galaxies than we anticipated. Dust can absorb and scatter light, making galaxies appear fainter and redder. If we're underestimating the amount of dust, we might be overestimating their distances based on redshift. However, even accounting for significant amounts of dust, the observed brightness of these galaxies remains difficult to explain. Another idea involves gravitational lensing. Massive objects like galaxies or black holes can bend the path of light, magnifying the images of objects behind them. If these early galaxies are being significantly lensed, their apparent brightness could be enhanced, making them seem closer than they actually are. However, gravitational lensing is a relatively rare phenomenon, and it's unlikely to explain the large number of unexpectedly bright galaxies observed by Webb. What if redshift is not the problem? What if the problem is our current method of calculating redshift itself? The standard method assumes that the redshift is purely cosmological, that it's solely due to the expansion of the universe. But what if there are other, non-cosmological contributions to the observed redshift? Some physicists have proposed that there could be intrinsic redshifts caused by the properties of the galaxies themselves. For example, if galaxies are ejecting matter at high speeds, this could create an additional redshift component that's not related to distance. However, there's currently no widely accepted physical mechanism that could produce significant intrinsic redshifts. Or perhaps we are wrong about the rate of expansion itself. We thought the lambda-CDM model, our standard model of cosmology, was pretty solid. It's been the foundation for understanding the universe's evolution for decades, but increasingly observations from James Webb are poking holes in it. It's not that the model is entirely wrong, but it might be incomplete or even based on some fundamentally flawed assumptions. The lambda CDM model, at its core, describes a universe dominated by dark energy, represented by the lambda, and cold dark matter, CDM. Dark energy is responsible for the accelerating expansion, while dark matter provides the extra gravity needed to explain the observed structure of galaxies and galaxy clusters. The model also incorporates the Big Bang theory, inflation, and the standard model of particle physics. It's a comprehensive picture built on a vast amount of observational evidence. Except now, some of that evidence is being questioned. One of the biggest challenges comes from the aforementioned abundance of early, massive galaxies. The lambda CDM model predicts that galaxy formation in the early universe should have been a slow, gradual process. Small galaxies should have formed first, merging over time to create larger ones. But Webb is showing us that massive, fully formed galaxies existed much earlier than expected. Within the first few 100 million years after the Big Bang, these galaxies are too numerous and too massive to easily reconcile with the standard model. Now, cosmologists are scrambling to figure out what's going on. Are there tweaks we can make to the lambda CDM model to accommodate these new observations, or do we need a more radical overhaul? One potential fix involves modifying our understanding of dark matter. The cold in cold dark matter refers to the fact that these particles are thought to be moving relatively slowly. However, some researchers are exploring the possibility of warm dark matter, which consists of particles that move faster. Warm dark matter would suppress the formation of small-scale structures, potentially allowing for the faster formation of larger galaxies. However, warm dark matter models also face their own challenges, and they may not be able to fully explain the observed abundance of early, massive galaxies. Another possibility involves modifying the properties of dark energy. The lambda in lambda CDM is often assumed to be a cosmological constant, a constant energy density that permeates all of space. However, some researchers are exploring alternative models of dark energy, such as quintessence, which proposes that dark energy is a dynamic field that evolves over time. These models could potentially affect the rate of expansion in the early universe, which in turn could influence the formation of galaxies. But what if the problem isn't with dark matter or dark energy? What if the problem lies in our understanding of gravity itself? The lambda CDM model is based on Einstein's theory of general relativity, which describes gravity as a curvature of space-time caused by mass and energy. General relativity has been incredibly successful at explaining a wide range of phenomena, from the motion of planets to the bending of light around massive objects. However, some physicists have proposed that general relativity might break down on very large scales or in the very early universe. Modified Newtonian dynamics, or MOND, is one such alternative theory of gravity. MOND proposes that gravity behaves differently at very low accelerations, such as those found in the outer regions of galaxies. MOND can explain the observed rotation curves of galaxies without invoking dark matter, and it has also had some success in predicting other aspects of galaxy formation. However, MOND is not without its problems, and it has difficulty explaining certain cosmological observations, such as the cosmic microwave background. And then there are more exotic ideas. Some physicists have even suggested that dark matter doesn't exist at all. Maybe what we perceive as dark matter is actually the result of undiscovered particles or forces that interact with ordinary matter in subtle ways. Perhaps our understanding of the fundamental laws of physics is simply incomplete. The James Webb Space Telescope is forcing us to confront these questions head-on. The sheer volume and quality of data it's producing is unprecedented, and it's painting a picture of the early universe that's far more complex and surprising than we ever imagined. The data reveals that we may need to revise our fundamental understanding of cosmology. The implications extend far beyond just tweaking a few parameters in the lambda CDM model. If we're forced to abandon or significantly modify our standard model, it could revolutionize our understanding of the universe's origin, evolution, and ultimate fate. It could even have implications for our understanding of fundamental physics. This isn't to say that the lambda CDM model is dead. It's still the best model we have, and it explains a vast amount of cosmological data. But the new observations from Webb are forcing us to acknowledge its limitations and to explore alternative possibilities. The scientific process thrives on challenges and revisions. When new data contradicts existing theories, it forces us to rethink our assumptions and to develop new, more accurate models. This is precisely what's happening now in cosmology, and it's an incredibly exciting time to be in the field. What's at stake? Nothing less than our understanding of the universe itself. And the search for answers leads us to a rather unexpected and perhaps unsettling possibility. There's a nagging problem that keeps popping up. The observed distribution of galaxies doesn't quite match what our simulations predict for a flat universe. We expect a certain level of homogeneity at large scales, but some observations suggest there might be more structure, more clumping, than the lambda CDM model allows. The idea of a curved universe isn't new. Einstein's theory of general relativity allows for three possibilities: a flat universe, a positively curved closed universe, or a negatively curved open universe. A flat universe is like an infinite plane, a closed universe is like the surface of a sphere, and an open universe is like a saddle. Our current understanding, based on measurements of the cosmic microwave background and other data, strongly favors a flat universe. But the James Webb Space Telescope is throwing a wrench into the works. The early galaxies it's observing appear surprisingly mature and clustered, which is hard to reconcile with a perfectly flat, homogeneous universe in its infancy. So, what if the universe isn't flat? What if it has a slight curvature, either positive or negative? This wouldn't necessarily invalidate general relativity, but it would require us to rethink some of our assumptions about the universe's initial conditions and its subsequent evolution. Consider a positively curved universe, like the surface of a sphere. In such a universe, parallel lines would eventually converge, and the density of matter and energy would be high enough to eventually halt the expansion and cause the universe to collapse in a big crunch. On the other hand, a negatively curved universe, like a saddle, would have parallel lines diverging, and the density of matter and energy would be too low to halt the expansion. The universe would continue to expand forever, becoming increasingly dilute and cold. The evidence shows that we're not heading toward a big crunch anytime soon, so let's focus on the possibility of a slightly negatively curved universe. This could explain the observed clustering of early galaxies, as a negative curvature would tend to amplify density fluctuations, leading to the formation of larger structures more quickly than in a flat universe. It's subtle, though. We're not talking about a universe shaped like a basketball or a saddle. The curvature, if it exists, would be very slight, almost imperceptible on small scales. But over vast cosmic distances, even a tiny curvature can have a significant effect on the distribution of matter and the evolution of the universe. Scientists discovered that if the universe is even slightly curved, it would have profound implications for our understanding of dark energy. Dark energy is the mysterious force that's causing the universe to accelerate its expansion. Its nature is one of the biggest unsolved problems in cosmology. If the universe is flat, dark energy is likely a cosmological constant, a constant energy density that permeates all of space. But if the universe is curved, dark energy could be something more complex, perhaps a dynamic field that changes over time. Measurements showed that a curved universe would also affect the way we interpret the cosmic microwave background. The CMB is the afterglow of the Big Bang, and its fluctuations provide a snapshot of the universe in its infancy. The pattern of these fluctuations depends on the geometry of the universe, so a curved universe would produce a slightly different pattern than a flat one. Here's what's wild. Some scientists have proposed that the apparent need for dark energy might be an illusion. If the universe is negatively curved, the geometry itself could mimic the effects of dark energy, causing the expansion to accelerate without the need for any exotic new force. The analysis continued, revealing that if we're misinterpreting the geometry of the universe, we could be completely wrong about the amount of dark matter it contains. Dark matter is the invisible stuff that makes up about 85% of the matter in the universe. We infer its existence from its gravitational effects on visible matter, but we don't know what it's made of. If the universe is curved, the amount of dark matter needed to explain the observed rotation curves of galaxies and the clustering of matter could be significantly less than we currently estimate. In fact, some models suggest that we might not need any dark matter at all. The curvature itself could be responsible for the gravitational effects we attribute to dark matter. This means the universe could be simpler than we thought. We might not need to invoke exotic new forms of matter and energy to explain its behavior. The geometry of space-time itself could be the key to understanding the universe's origin, evolution, and ultimate fate. But before we throw out the lambda CDM model, it's important to remember that the evidence for a curved universe is still tentative. The James Webb Space Telescope is providing us with incredibly valuable new data, but we need more observations and more sophisticated analyses to confirm or refute this possibility. The implications extend far beyond just cosmology. If the universe is curved, it would challenge our fundamental understanding of physics. It would force us to rethink our assumptions about the nature of space, time, and gravity. It could even open up new avenues of research in areas like quantum gravity and string theory. And then, of course, there's the philosophical dimension. A curved universe would challenge our intuitive understanding of the cosmos. It would remind us that our perception of reality is limited and that the universe may be far stranger and more wonderful than we can imagine. This isn't just about tweaking a few parameters in a model. It's about questioning our fundamental assumptions about the nature of reality. It's about pushing the boundaries of human knowledge and venturing into the unknown. Webb just revealed something massive. Not a galaxy, not a nebula, but a potential shift in the very engine driving the universe's expansion. Dark energy. We've always pictured dark energy as this constant, unwavering force, a kind of cosmic thermostat keeping the expansion rate steady. It's built into the lambda CDM model as a cosmological constant, meaning its density stays the same as the universe expands. Think of it like this. Imagine blowing up a balloon. The amount of air you're putting in, dark energy, stays the same even as the balloon gets bigger. The universe expanding. Simple, right? Maybe not. What if dark energy isn't constant? What if it's dynamic, changing its strength over time? This is where the potential curvature of the universe comes back into play. If space is curved, the equations that govern dark energy become far more complex. The relationship between dark energy, matter, and the expansion. Rate isn't so straightforward anymore. Instead of a constant push, dark energy could be weakening, becoming less influential as the universe ages. Or, even more radically, it could be oscillating, sometimes accelerating the expansion, sometimes slowing it down. Imagine a car accelerating, then decelerating, then accelerating again. That's the kind of behavior we might be looking at. Why would this happen? That's the million-dollar question. One possibility lies in the realm of quintessence. Quintessence is a hypothetical form of dark energy that isn't constant but changes over time, behaving more like a field than a fixed quantity. Think of it as a dynamic fluid that permeates the universe, its density and pressure fluctuating depending on its interactions with other components of the cosmos. The James Webb Telescope's ability to see the universe at different points in its history is crucial here. By observing the light from distant galaxies, Webb can essentially look back in our time, measuring the expansion rate at different epochs. If dark energy is constant, those measurements should align with the predictions of the lambda CDM model. But if it's changing, we should see deviations, subtle shifts in the expansion rate that point to a dynamic dark energy component. These deviations are incredibly subtle, and that's why they've been so hard to detect. We're talking about tiny fractions of a percent difference in the expansion rate, buried beneath layers of cosmic dust and observational uncertainties. But Webb's precision is unparalleled. It can see further and more clearly than any telescope before it, allowing us to measure the expansion rate with unprecedented accuracy. Consider the implications if dark energy is indeed dynamic. It would completely upend our understanding of the universe's fate. A constant dark energy implies that the universe will continue to expand forever, eventually becoming cold, empty, and desolate. This is the big freeze scenario, but a weakening dark energy opens up other possibilities. If dark energy weakens enough, gravity might eventually overcome it, causing the expansion to slow down and eventually reverse. This could lead to the big crunch, where the universe collapses in on itself, ultimately shrinking back to an infinitely dense point. It's a far more dramatic and perhaps unsettling end to the story. Or perhaps dark energy could simply fade away, leaving the universe to expand at a slower, more manageable pace. This scenario, sometimes called the Big Rip, would still result in a cold and empty universe, but it would avoid the violent cataclysm of the Big Crunch. The shape of the universe itself plays a key role here. If the universe is flat, a dynamic dark energy requires exotic physics beyond the standard model. But if the universe is curved, then a dynamic dark energy becomes more natural, potentially arising from the geometry of space-time itself. Think of it like a stage play. The actors, matter and energy, perform their roles, but the stage itself, the geometry of the universe, influences their movements and interactions. A curved stage can create unexpected effects, altering the way the actors behave and changing the course of the play. Measurements showed that understanding dark energy also requires understanding how it interacts with dark matter. Some theories propose a direct interaction between these two mysterious components, a kind of cosmic dance where they exchange energy and momentum. This interaction could also manifest as a change in the effective strength of dark energy over time. Scientists discovered that Webb's data might give us clues about the nature of dark matter itself. If dark matter particles interact with each other, or with ordinary matter, they could leave subtle fingerprints on the cosmic microwave background, the afterglow of the Big Bang. These fingerprints could then be detected by Webb, providing us with a new window into the dark sector of the universe. Here's what's wild. If dark energy is dynamic, it could also solve one of the biggest puzzles in cosmology: the Hubble tension. The Hubble tension refers to the discrepancy between the expansion rate of the universe measured locally using supernovae and the expansion rate measured from the cosmic microwave background. These two measurements disagree by a significant amount, and no one knows why. A dynamic dark energy could potentially resolve this tension by allowing the expansion rate to vary over time, reconciling the local and distant measurements. It's like having a flexible ruler that stretches and shrinks, allowing us to measure the universe more accurately. The implications extend to our understanding of fundamental physics. If we confirm that dark energy is indeed dynamic and linked to the curvature of space, it would point to the need for a new theory of gravity, one that goes beyond Einstein's general relativity. It could open the door to exploring extra dimensions, modified gravity, and other exotic concepts that have been relegated to the realm of theoretical speculation. The analysis continued, revealing that we might need to rethink our assumptions about the early universe. The standard model of cosmology assumes that the universe underwent a period of rapid inflation shortly after the Big Bang, a brief but intense burst of expansion that smoothed out the universe and seeded the formation of galaxies. But a curved universe with a dynamic dark energy might challenge this picture. Perhaps the early universe was more chaotic and less uniform than we thought. Perhaps inflation wasn't as necessary or as powerful as we currently believe. These are radical ideas, but they are worth considering in light of the new evidence from Webb. And then there's the philosophical angle. The idea that the universe is curved and that dark energy is changing challenges our intuitive understanding of reality. It reminds us that the universe is far stranger and more complex than we can imagine, and that our current models are just approximations of a deeper, more mysterious reality. It forces us to confront the limits of human knowledge and to embrace the unknown. This changes our perception of the entire cosmos. The Hubble tension, that nagging discrepancy between different measurements of the universe's expansion rate, suddenly looks different in this light. For years, astronomers have been scratching their heads trying to reconcile the expansion rate of the nearby universe with that predicted by the cosmic microwave background, CMB, the afterglow of the Big Bang. Measurements of supernovae in nearby galaxies suggest a faster expansion rate than what the CMB implies. This tension has fueled countless papers and conferences, with scientists proposing everything from new particles to modified gravity to explain the mismatch. But what if the problem isn't new physics, but rather our assumption that the universe is flat? A curved universe, especially one with a dynamic dark energy, could naturally reconcile these disparate measurements. The curvature could affect the way we interpret distances and redshifts, leading us to overestimate the expansion rate in the local universe. Think of it like trying to measure the distance between 2 points on a globe using a flat map. You'll inevitably get it wrong because you're ignoring the curvature of the surface. The Webb telescope, with its unprecedented precision and ability to see the most distant objects, is providing us with new data that could finally resolve this tension. By measuring the distances to far-off galaxies and quasars with greater accuracy, Webb can help us map the geometry of the universe and determine whether it is indeed curved. But the implications don't stop there. If the universe is curved, it would also affect our understanding of dark energy, the mysterious force that is accelerating the expansion of the universe. Currently, we assume that dark energy is a constant, a kind of uniform pressure that permeates all of space. But a curved universe could imply that dark energy is dynamic, meaning that its strength varies over time. This dynamic dark energy could be linked to the curvature of space, with the two influencing each other in a complex and intertwined way. Imagine a balloon that is both expanding and changing shape at the same time. The expansion and the shape are not independent, but rather are linked by the properties of the balloon itself. The idea that dark energy is dynamic also has implications for the fate of the universe. If dark energy remains constant, the universe will continue to expand forever, becoming increasingly cold and empty. But if dark energy is dynamic, its strength could eventually weaken, causing the expansion to slow down or even reverse. In this scenario, the universe could eventually collapse in on itself in a big crunch, a mirror image of the Big Bang. Or, dark energy could become negative, causing the universe to oscillate between expansion and contraction in an endless cycle. These are just speculations, of course, but they highlight the profound implications of a curved universe and a dynamic dark energy. It's a subtle shift, but profound. The standard model of cosmology, which has been our guiding framework for decades, assumes that the universe is flat and that dark energy is constant. But the Webb telescope is challenging these assumptions, forcing us to reconsider our most basic ideas about the nature of the cosmos. This also brings into question the very precise measurements of the cosmic microwave background. Are we interpreting that data correctly if we're imposing a flat geometry on a curved reality? It could be that some of the anomalies and puzzles in the CMB data are actually hints of curvature that we've been overlooking. Consider the implications for inflation. The inflationary epoch, that incredibly brief period of exponential expansion in the very early universe, is invoked to explain the observed flatness and homogeneity of the cosmos. But if the universe isn't flat to begin with, do we even need inflation? Perhaps there were other mechanisms at play in the early universe that we haven't yet considered. Processes that could have shaped the universe without requiring a period of rapid inflation. It's a radical idea, but one that's worth exploring in light of the new evidence. And then there's the philosophical dimension. For centuries, humans have pondered the shape and fate of the universe. We've built elaborate models and theories, but we've always been limited by our observations and our assumptions. Now, with the Webb telescope, we're finally able to see the universe in a new light, to challenge our assumptions, and to glimpse the true nature of reality. It's a humbling experience to realize that our current understanding of the universe may be incomplete or even wrong. But it's also an exciting one because it opens up new avenues of exploration and discovery. It reminds us that science is a process of continuous refinement, of questioning our assumptions, and of embracing the unknown. What if the curvature isn't uniform? What if some regions of space are more curved than others? This could lead to even more complex and fascinating cosmological models, ones that challenge our understanding of gravity and space-time. It opens up the possibility of exploring new physics, new dimensions, and new realities. The Webb data could point us to a new theory of quantum gravity, one that reconciles Einstein's general relativity with quantum mechanics, the two pillars of modern physics. Such a theory could explain the nature of dark energy and dark matter, the origin of the universe, and the ultimate fate of the cosmos. It may sound like science fiction, but it's the kind of speculation that's fueled by real data and real observations. The Webb telescope is not just a tool for taking pretty pictures. It's a portal to a new understanding of the universe, and it's forcing us to confront the possibility that everything we thought we knew may be an illusion. You've been given a comforting lie about the universe. The smooth, uniform cosmos we picture in our heads, the one predicted by our standard models. It might not exist. The Webb telescope is showing us galaxies that formed far earlier than we thought possible. They're too big, too bright, and too mature for their supposed age. This throws a wrench into our understanding of how galaxies evolve, how quickly they can form, and the conditions that were present in the early universe. Our current simulations struggle to reproduce these observations. They predict a more gradual process of galaxy formation, with smaller, less developed galaxies populating the early universe. But the Webb data paints a different picture, one of rapid growth and surprising complexity. This isn't just a minor tweak to our models, it's a fundamental challenge. It suggests that we're missing something crucial in our understanding of the underlying physics. Perhaps there are processes at play that we haven't yet accounted for, mechanisms that can accelerate galaxy formation and allow these behemoths to arise in the early universe. Consider the role of dark matter. We know that dark matter makes up a significant portion of the universe's mass, and it plays a crucial role in the formation of cosmic structures. But what if our understanding of dark matter is incomplete? What if it interacts with ordinary matter in ways we haven't yet discovered? Such interactions could potentially influence the formation of galaxies, leading to the accelerated growth we're seeing with Webb. Or perhaps the problem lies with our understanding of star formation. The rate at which stars form in a galaxy can have a significant impact on its overall evolution. If star formation was more efficient in the early universe than we currently believe, it could explain the rapid growth of these early galaxies. Scientists discovered that supermassive black holes could also be playing a more significant role than previously thought. These behemoths, lurking at the centers of galaxies, can influence the surrounding environment in profound ways. They can trigger bursts of star formation, regulate the flow of gas and dust, and even suppress the formation of new stars. If supermassive black holes were more prevalent or more active in the early universe, they could have significantly altered the course of galaxy evolution. Measurements showed that feedback mechanisms, processes that regulate star formation and black hole growth, might be different in the early universe. These mechanisms can either promote or suppress the formation of new stars, and they can also influence the growth of supermassive black holes. If these feedback mechanisms were weaker in the early universe, it could have allowed galaxies and black holes to grow more rapidly. The analysis continued, revealing the need to re-evaluate the initial conditions of the universe. Our current models assume a certain distribution of matter and energy in the early universe. But what if that distribution was different? What if there were regions of space that were denser or more energetic than we currently believe? Such variations could have seeded the formation of these early galaxies, allowing them to grow more quickly than expected. This means new simulations and models are desperately needed. We need to incorporate these new findings into our theoretical frameworks, to explore different scenarios and to see if we can reproduce the observations made by the Webb telescope. This will require a collaborative effort, bringing together experts in galaxy formation, cosmology, and particle physics. It will also require a willingness to challenge our assumptions and to embrace new ideas. The implications extend beyond just galaxy formation. If our understanding of galaxy evolution is flawed, it could also affect our understanding of the universe as a whole. It could challenge our understanding of dark matter, dark energy, and even the fundamental laws of physics. Here's what's wild. The Webb telescope is not just confirming our existing theories, it's actively challenging them. It's forcing us to confront the possibility that our current understanding of the universe is incomplete or even wrong. And that's exactly what science is supposed to do. Our entire picture of the universe is likely incomplete. And a statistical tool called Bayesian analysis is now pointing us in a very specific direction, one that could rewrite the textbooks. Let's examine how this works. Bayesian analysis is, at its heart, a way of updating our beliefs in light of new evidence. You start with a prior belief, a hypothesis about how the universe works, and then you feed in new data. The analysis then spits out a posterior belief, a revised hypothesis that takes the new data into account. The bigger the mountain of evidence, the stronger the posterior belief. Now, in the context of the James Webb data, Bayesian analysis is being used to assess how well our existing cosmological models fit the new observations of these early galaxies. Are our models a good fit? Is there some wiggle room? Or are they fundamentally wrong? The early results are, well, they're unsettling depending on who you ask. Consider this. The Webb data is so precise, so detailed, that it's allowing astronomers to test their models in ways they never thought possible. It's like taking a magnifying glass to a blurry photograph. Suddenly you can see all the flaws, all the imperfections that were previously hidden. And those flaws, those imperfections, are adding up. The Bayesian evidence is suggesting that our current models are struggling to explain the rapid formation and evolution of these early galaxies. The sheer number of massive galaxies, their unexpectedly high star formation rates, and their surprising chemical compositions all point to a universe that behaved differently in its infancy than we previously thought. The data reveals that the posterior probability for some alternative models is significantly higher than for our standard model, which means, statistically speaking, that these alternative models are more likely to be correct, given the available evidence. What kind of alternative models are we talking about? Well, that's where things get interesting. Some researchers are exploring modifications to the standard model of cosmology, tweaking parameters like the amount of dark matter or the properties of dark energy. Others are considering more radical departures, such as alternative theories of gravity or models with variable fundamental constants. Think about it. The fundamental constants of physics, things like the speed of light or the gravitational constant, are assumed to be constant throughout the universe and throughout time. But what if they weren't? What if they varied slightly in the early universe? Such variations could have profound effects on galaxy formation, potentially allowing galaxies to grow more quickly and efficiently than predicted by our current models. It's a controversial idea, no doubt, but the Webb data is forcing scientists to consider all possibilities, no matter how outlandish they may seem. And it's not just about tweaking parameters or modifying existing theories. Some researchers are even questioning the fundamental assumptions that underpin our cosmological models. For example, our current models assume that the universe is homogeneous and isotropic on large scales, meaning that it looks roughly the same in all directions and at all locations. But what if this assumption is wrong? What if there are large-scale structures or anisotropies in the universe that we haven't yet detected? Such structures could have influenced the formation of early galaxies, creating regions of space where galaxies could grow more rapidly than in other regions. Further examination revealed something even more profound: the implications for dark matter. Our current models rely heavily on the existence of dark matter to explain the formation of galaxies and large-scale structures. But the Webb data is raising questions about the role of dark matter in the early universe. If galaxies formed more quickly and efficiently than expected, does that mean that dark matter was more abundant in the early universe? Or does it mean that dark matter interacted with ordinary matter in a different way than we currently believe? Or does it mean we have dark matter wrong? These are open questions, and the answers are far from clear. But one thing is certain: the Webb data is forcing us to rethink our understanding of dark matter and its role in the evolution of the universe. This means that the Webb telescope, by peering back into the early universe, is essentially acting as a cosmic time machine, allowing us to test our theories in ways that were never before possible. And what it's showing us is that our current understanding of the universe is likely incomplete, or even wrong, in some fundamental ways. And then there's the possibility that what we perceive as the universe's shape, its very structure, is itself an illusion, a trick of perspective based on incomplete data and flawed assumptions. The Bayesian evidence is suggesting that we've been looking at the cosmos through a distorted lens, and that the true picture is far more complex and nuanced than we ever imagined. This isn't just about tweaking a few parameters in our models. This is about questioning the very foundations of our understanding of the universe. It's about confronting the possibility that our most cherished theories are wrong, and that we need to start from scratch to build a new and more accurate picture of the cosmos. The implications extend far beyond the realm of cosmology. If our understanding of the universe is flawed, it could also affect our understanding of other areas of physics, such as particle physics and quantum gravity. It could even challenge our understanding of the fundamental laws of nature. Here's what's wild. The Webb telescope is not just providing us with new data, it's providing us with a new way of thinking about the universe. It's forcing us to be more open-minded, more creative, and more willing to challenge our assumptions. And that's exactly what science is supposed to do. This could even impact our search for extraterrestrial life. If the conditions for galaxy formation and evolution were different in the early universe, it could mean that the conditions for the emergence of life are also different than we thought. It could mean that life is more common or more rare than we currently believe. It could mean that life exists in forms that we haven't even imagined. 87% of the universe is invisible to us. Dark matter and dark energy, these mysterious components, completely dwarf everything we can directly observe with even the most powerful telescopes. That means our understanding is based on just a sliver of reality, and we're trying to extrapolate the whole picture from that tiny piece. So, what about future observations and tests? Where do we go from here? Well, the James Webb is just getting started. We're only scratching the surface of what it can do. Planned observations will target even earlier galaxies, pushing the boundaries of what we can see to within the first few 100 million years after the Big Bang. This will give us a much clearer picture of galaxy formation in its earlier stages, helping us to refine our models and test our theories. And it's not just about seeing further back in time, it's also about observing the universe in greater detail than ever before. Webb's infrared capabilities allow it to penetrate the dust clouds that obscure our view of many galaxies, revealing the hidden processes that are driving their evolution. We can actually peer inside these galactic nurseries and watch stars being born, gaining invaluable insights into the physics of star formation. Consider also the upcoming Extremely Large Telescope, or ELT, currently under construction in Chile. With a primary mirror nearly 40 meters in diameter, the ELT will be the largest optical telescope in the world. Its sheer size will allow it to gather unprecedented amounts of light, enabling us to study the faintest and most distant objects in the universe with incredible precision. The ELT will complement Webb's observations by providing higher resolution images and spectra, allowing us to probe the properties of individual stars and gas clouds within these early galaxies. This will give us a much more detailed understanding of the chemical composition and physical conditions of the early universe. Further examination revealed something else too. These future telescopes aren't just about seeing further and clearer, they're also about testing our fundamental understanding of physics. By observing the universe at different wavelengths and with different instruments, we can look for subtle deviations from the predictions of our current theories. For example, we can test Einstein's theory of general relativity by observing the way light is bent by massive objects, searching for any discrepancies that might point to new physics. And then there's the search for dark matter and dark energy. These mysterious substances make up the vast majority of the universe, but we still have no idea what they are. Future observations will focus on mapping the distribution of dark matter in galaxies and clusters of galaxies, hoping to uncover clues about its nature. We can also use telescopes to measure the expansion rate of the universe with greater precision, which could shed light on the properties of dark energy. Here's what's wild. It's not just about telescopes. Particle accelerators like the Large Hadron Collider, or LHC, at CERN also play a crucial role in testing our understanding of the universe. By colliding particles at incredibly high energies, the LHC can recreate the conditions that existed in the early universe, allowing us to probe the fundamental laws of physics at their most extreme. These experiments could reveal new particles and forces that could help us to understand dark matter, dark energy, and the other mysteries of the cosmos. The analysis continued, but it goes beyond even that. Gravitational wave detectors like LIGO and Virgo are opening up a completely new window on the universe. By detecting the ripples in space-time caused by colliding black holes and neutron stars, these detectors are providing us with a completely new way to study the most violent and energetic events in the cosmos. And as these detectors become more sensitive, they could even detect gravitational waves from the Big Bang itself, giving us a direct glimpse into the very beginning of the universe. The implications extend to space-based observatories dedicated to specific tasks, like mapping the cosmic microwave background, the afterglow of the Big Bang. These missions can measure the temperature fluctuations in the CMB with incredible precision, providing us with a wealth of information about the early universe. These measurements can be used to test our models of inflation, the period of rapid expansion that is believed to have occurred in the first fraction of a second after the Big Bang. Meanwhile, a completely new approach is computational cosmology. As telescopes gather more and more data, and particle physics experiments provide more and more constraints on the fundamental laws of physics. Supercomputers are able to run increasingly sophisticated simulations of the universe. These simulations can be used to test our theories of galaxy formation, dark matter, and dark energy, and to make predictions about the future evolution of the universe. The data reveals that by comparing the results of these simulations with real observations, we can refine our models and gain a deeper understanding of the complex processes that have shaped the cosmos. It's iterative: observation, simulation, comparison, refinement. Consider this: it's not just about building bigger and better telescopes. It's also about developing new techniques for analyzing the data that they produce. Machine learning and artificial intelligence are playing an increasingly important role in cosmology, allowing us to extract meaningful information from vast datasets that would be impossible to analyze by hand. These techniques can be used to identify patterns in the distribution of galaxies, to classify different types of astronomical objects, and to search for new and unexpected phenomena. All this new data, all these new approaches, they all converge on one central point. We are on the cusp of a new era in cosmology. An era where our understanding of the universe will be transformed by a flood of new data and new ideas. An era where we will finally be able to answer some of the most fundamental questions about the cosmos. An era where we might finally discover the true shape of the universe and our place within it. But there's a flip side to all this excitement. The more we learn, the more we realize how much we don't know. And that's okay. That's the nature of science. It's a process of continuous discovery where we are constantly challenging our assumptions and refining our theories. And as we continue to explore the universe, we can be sure that we will encounter even more surprises and mysteries along the way. What if the real problem isn't the data but how we're interpreting it? We've spent decades building a cosmic story, a narrative woven from observations, theories, and simulations. But what if we've been focusing on the wrong details, emphasizing certain aspects while neglecting others? What if the shape we're looking for isn't some grand geometric form, but something far more subtle and nuanced? The James Webb Space Telescope, with its unprecedented ability to peer into the distant universe, is providing us with a flood of new information. But data alone isn't enough. We need to be able to make sense of it, to fit it into our existing framework of understanding. And that's where things get tricky. Our current cosmological models are based on a number of assumptions about the nature of dark matter, dark energy, and the initial conditions of the universe. These assumptions have been remarkably successful in explaining many of the observed features of the cosmos. But they also lead to some persistent puzzles and discrepancies. For instance, the observed distribution of galaxies on large scales doesn't quite match the predictions of our simulations. There are also tensions between different measurements of the Hubble constant, the rate at which the universe is expanding. These discrepancies could be due to a number of factors. It's possible that our measurements are simply inaccurate or that our models are incomplete. But it's also possible that there's something fundamentally wrong with our understanding of the universe. Maybe dark matter isn't what we think it is. Maybe dark energy is evolving over time. Or maybe our assumptions about the initial conditions of the universe are incorrect. The challenge is to figure out which of these possibilities is the most likely, and that requires us to be open to new ideas, to challenge our existing assumptions, and to be willing to rewrite the cosmic story if necessary. The data reveals we have to consider every option. This isn't just about tweaking the parameters of our models. It's about questioning the very foundations of our understanding. Are we sure that general relativity is the correct theory of gravity on cosmological scales? Are we sure that the universe is homogeneous and isotropic, as we usually assume? Are we sure that the laws of physics are the same everywhere in the universe? These are difficult questions, and there are no easy answers. But they are questions that we need to address if we want to make progress in cosmology, and the James Webb Space Telescope is giving us the tools to do so. The analysis continued. By providing us with a wealth of new data, Webb is forcing us to confront these fundamental questions. It's challenging us to think more creatively, to develop new theories, and to explore new possibilities. And that's exactly what science is all about. Scientists discovered the potential for a paradigm shift. Maybe the true shape isn't a shape at all in the traditional sense. Maybe it's a set of relationships, a network of interactions, a complex system that defies simple geometric description. Consider this. Imagine trying to describe the shape of a forest. You could try to measure the height and width of each tree, but that wouldn't really capture the essence of the forest. The forest is more than just the sum of its parts. It's a complex ecosystem with intricate connections between the trees, the plants, the animals, and the soil. Similarly, the universe may be more than just the sum of its galaxies, its dark matter, and its dark energy. It may be a complex system with intricate connections between all of its components. And to understand the true shape of the universe, we may need to look beyond the traditional tools of geometry and physics. The implications extend to how we even do cosmology. The simulations we run, the observations we prioritize, the very language we use to describe the cosmos, all of it may need re-evaluation. If we've been chasing the wrong shadows, focusing on the wrong variables, then all our conclusions, built carefully one upon another, start to wobble. It's unsettling, certainly, but it's also exhilarating. It means that there are still profound discoveries waiting to be made, that the universe is still full of surprises, and that we, as humans, have the capacity to unravel its mysteries. The journey to understand the universe is a long and winding one. There will be setbacks and surprises along the way. But if we remain open to new ideas, if we continue to challenge our assumptions, and if we never lose our sense of wonder, we can be confident that we will eventually arrive at the truth. Or at least a closer approximation of it. And who knows? Maybe, just maybe, the true shape of the universe is something that we can't even imagine yet. Perhaps it's something that will require us to develop entirely new ways of thinking, entirely new ways of seeing. Perhaps it will require us to transcend the limitations of our own minds, to glimpse a reality that is far stranger and more wonderful than we ever thought possible. Meanwhile, the quest continues, and as you follow that quest, remember to stay curious.